Today, we're going to do one sample confidence intervals for P, the population proportion. First, we were going to remember that the basic setup for any confidence interval in this class is point estimate plus or minus critical value times the standard error of that point estimate, or PE plus or minus CV times SE. So if you just remember PE for point estimate, CV for critical value, and SE for standard error, you'll be good to go. And you'll just know the basic form for any confidence interval that we'll be building. So in a given scenario, it just remains to determine the appropriate PE, CV, and SE to use, and then we can proceed from there. And so for the scenarios that we're going to use for the 4 examples in this video, we're going to use the Skittles example. This example 1 is going to be the baseline example that we're going to keep referring back to when we do the other upcoming examples. So remember that we've got, in this example, 100 Skittles candies for a sample, and 23 of those candies are red. And we want to find a 95% confidence interval, or CI, for the true proportion of red Skittles candies. And so this is just going to be the basic setup, the basic scenario for comparison when we set up other confidence intervals later on. So first off, we're trying to find the true proportion of red Skittles. So that's the parameter of interest, P, the true proportion of red Skittles. So this is a population parameter. Because we're dealing with a true proportion, and it's a proportion that's unknown. We don't know how many Skittles Wrigley actually manufactures, or what proportion that total number of red Skittles constitutes of all Skittles made. But we can try to get at it by taking a sample, and so that's what we've done. We have a sample of size 100, so this is N, our sample size. And 23 of those are red, so this is X, the number of successes. And finally, the last piece of information we have here is this 95%. We want a 95% confidence interval. So we have all the information we need to build this confidence interval of interest. To estimate a proportion, we need our point estimate. And our point estimate, or our best guess for the true proportion, is our sample proportion, and that's P hat. And here we're not given P hat directly, we have to calculate it. So P hat here is just that, again, that X over N, or 23 over 100, which equals 0.23. This is our sample proportion. If I were to take a different sample, I might get a different sample proportion. The next thing I need to do is figure out my critical value. In order to use the normal distribution, or the Z distribution, I have to check my sample size. I have to have at least 15 successes and at least 15 failures. Normally we would do N times P, the true proportion, and N times 1 minus P, the true proportion again, but we don't know the true proportion. And so instead we're going to use P hat. So we're going to do 100 times 0.23 and 100 times 1 minus 0.23, and these are both greater than 15. So we're good to go. We can use a Z critical value. Yay! So our critical value is going to be Z alpha over 2. What is alpha? Well, alpha, remember, is 1 minus our confidence level, and our confidence level is 0.95. Because we want 95% confidence, so that confidence level is 0.95. So that means alpha in this case is 0.05. So alpha over 2 equals 0.025. So Z sub alpha over 2 equals Z sub 0.025. And we get this from the normal table. To find our alpha, or to find our z-score, we find the probability of interest in the body of the table. So we want z sub 0.025. And that means that this is going to be the z-score that has 0.025 probability less than it. So we're looking for this z value. So if we come in here, we're going to look for our z value, and we see that 0.025 is right here. So we come out this way and up this way, and we see that this z equals negative 1.96. So again, we have negative 1.9 here and 0.06 here, so that gives us a z of negative 1.96 for our critical value. So coming back here, our critical value is negative 1.96. So now all we need is our standard error. And remember, this is the standard error of our point estimate, which in this case is p hat. And the standard error of p hat is p hat, 1 minus p hat, all over n. We take the square root of that fraction. And again, if we knew the true proportion, those p hats would be p's, but because we don't know that true proportion, we use p hat to find the standard error. Well, p hat is 0.23. 1 minus p hat, it's going to be 1 minus 0.23, and n is 100. And when we work this out, we get a standard error of 0.0421. So we put all these three things together. We've got our PE plus or minus CV times the standard error, or p hat plus or minus our z alpha over 2 times the square root of p hat, 1 minus p hat over n. So we've got our formula, we need our substitution, so 0.23 plus or minus negative 1.96 times 0.0421. And when we solve for this, our confidence interval, or our 95% confidence interval, is 0.148 to 0.312. So again, our 95% confidence interval for the true proportion of red Skittles is 0.148 to 0.312. This is a range of plausible values or believable values for P based on this sample. So I'm 95% confident that that true proportion is contained by this interval. Now let's consider this next example. Say instead we have a sample of 100 Skittles candies and 23 of those candies are red, but now we want to find a 99% confidence interval for the true proportion of red Skittles candies. So we've got the same sample, 100 Skittles, 23 are red, but we want a 99% confidence interval. More confidence sounds great. I would love to be more confident in my estimate. So let's find that. Well, our PE, we're still estimating that true proportion, so our PE is unchanged. We're still using p hat, and that's still going to be 23 over 100. So that's going to be 0.23. And I'm going to make a note to ourselves that this is unchanged from problem 1. And I'm going to come down and say, well, what's our standard error? And our SE, well, that's just going to be the standard error of p hat. That's our standard error of p hat, and that's the square root of p hat, 1 minus p hat over n. And that's just going to be the same thing as before because p hat is unchanged, so that's going to be 0.0421, also unchanged. It's nice when we save ourselves some work like this. So because we've changed our confidence level, the only thing that's changed here is our critical value. So we're still using a z, because our sample size hasn't changed, our sample proportion hasn't changed, so we'll still have at least 15 successes and at least 15 failures. But our confidence level has changed, so we have to find this instead. So our z alpha over 2 is going to be a new value. And here, alpha equals 1 minus 0.99, or 0.01. That means alpha over 2 is going to be 0.005. So on the normal table, we're looking for alpha over 2 equals 0.005. And so we know that's going to be a small probability, so that's going to have a small or a very negative z-score. So we're going to look over here, and we're going to see a z-score. We see that we've got 0.0051 and 0.0049. Now I'm going to go with this 0.0049 just because I feel like it. Now remember, never average z-scores. So this 0.0049 gives me a z-score here, here. So I've got negative 2.58. So z alpha over 2, or z of 0.005, that is equal to negative 2.58. And graphically, that means that I have a z-score with 0.005 probability less than it, and that z-score is negative 2.58. So coming back to my work, my z of 0.005 is negative 2.58. And I again have all the pieces I need to get my confidence interval for that true proportion. So my 99% confidence interval for P is P hat plus or minus z alpha over 2 times the standard error of P hat, which is P hat 1 minus P hat over n, and I take the square root of that whole fraction. And then I can plug in because I have all these terms. So it's going to be 0.23 plus or minus that z-score, that negative 2.58, times our standard error of 0.421. And when I solve for this, my confidence interval now is 0.121 to 0.339. We can see this is still a range of plausible values, but it is a wider range. In example 1, our confidence interval was 0.148 to 0.312. This was 95% confidence. This is 99% in example 2. When you increase your confidence, all that changed in this problem was our critical value, and increasing the confidence increases our critical value. It got bigger. So increasing our confidence widens our interval, all other things equal. So let's consider this next example. Say you have a sample now of 1,000 Skittles candies and 230 of them are red. Now we're going to find we're back to a 95% confidence interval for that true proportion of red Skittles candies. So our PE, that's still going to be P hat equals x over n, the number of successes over the total number of observations, but now x is 230 and n is 1,000, but it gives us the same sample proportion. Our proportion is still 0.23. So this is unchanged from problem 1. Our critical value, well, this is just going to be z equals alpha over 2, which is z of 0.025, because we know that from a 95% confidence interval from problem 1, and that's negative 1.96, and this is from problem 1. So this is unchanged. Our standard error, well, this is the standard error of P hat, and that's that square root of P hat, 1 minus P hat over n, And so we're going to go along, we're going to do that square root of 0.23, 1 minus 0.23, but now n is 1,000. So our standard error is 0.0133, and this is smaller than in number 1. So we have the same point estimate, we have the same critical value, but we have a smaller standard error than we did in our previous example. So our 95% confidence interval is going to still be that p hat plus or minus z alpha over 2 times the square root of p hat 1 minus p hat over n. And we're going to plug in, so 0.23 plus or minus negative 1.96 times now 0.0133 for our standard error. And our confidence interval is 0.204 to 0.256. This is a narrow interval relative to that CI from 1, in which case we had 0.148 to 0.312. So, increasing sample size narrows the interval, all other things being equal. In this last example, we have a sample of size 100, so we're back to our original sample size, but now we have 77 red candies, and we're going to find again a 95% confidence interval. So we're going to see what happens now. So our PE, that's p hat, that's going to be 77 over 100, or 0.77. So this is different than problem 1. Our CV, this is z alpha over 2, alpha equals 0.05 for our 95% confidence interval. So this is just going to be that z of 0.025, negative 1.96 from problem 1. So this is unchanged. And finally, our standard error, well, this is the standard error of our point estimate, or p hat. So that's going to be the square root of p hat, 1 minus p hat over n. So that's the square root of 0.77 times 1 minus 0.77 divided by 100. And when we work this out, we get a standard error of 0.0421, and this is deliberately unchanged from problem 1. So we have the same critical value, the same standard error from problem 1. All that's changed is our point estimate. So we can set up our 95% confidence interval for the true proportion. That's going to be p hat plus or minus z alpha over 2 times the square root of p hat 1 minus p hat divided by n. And we plug in. So now our p hat is 0.77 plus or minus our critical value of negative 1.96 times our standard error of 0.0421. And when we work this out, our confidence interval is 0.687 to 0.853. So this is the same width as number 1, which it should be because we had the same critical value, the same standard error, but it is shifted relative to our interval in 1. We have a different point estimate, which means the center of the CI has changed. Our best guess is different. So what does this mean visually? So here is a web app that will calculate confidence intervals for you and gives you kind of visual representation of what's going on. So let's consider our first example where we had a sample size of 100 and we had 23 successes. We're building a confidence interval with 95% and we're doing an interval, so we want to estimate both a lower and an upper bound. Here we have our successes, so we had a 23% success rate and we had a 77% failure rate. So here we've got red Skittles and not red Skittles in our sample. Here are our sample statistics. This is just another way of summarizing it. We've got a bar chart summarizing it, we've got a table summarizing it. We've got the estimate of our population proportion, so we have our point estimate, the standard error that we calculated, which is the same as before, we have that 0.0421, and this is that margin of error. So if we had ever actually just looked at that margin of error, which is the CV times the SE, we would have gotten that 0.0825. So that's what we add and subtract from our point estimate to calculate our confidence interval. So our confidence interval, we end up with a confidence interval of 0.1475 to 0.3125. When we did it, we rounded to the third decimal place and ended up with a confidence interval of 0.148 to 0.312, and that's not bad. So here what we have, proportions can be anywhere between 0 and 1. So here's a number line representing that possible range. Our confidence interval, well, we got a sample statistic of p-hat of 0.23. So this square here on the line, that's the sample statistic, that's our p-hat. And these whiskers that extend from that line, this is the range of that confidence interval. Now let's see what happens when we change our confidence level to 99% like we did in example 2. Those bars, or those whiskers, got longer. They're going to cover a wider range of that possible values of the proportion. If we instead have a sample size of 1,000, like we did in example 3, and we have 230 successes so that our sample proportion is the same with a 95% confidence level, we see that our sample p-hat stays the same, but those whiskers get quite a bit smaller. Our whiskers are tiny relative to what they had been when we had only 100 observations. And then finally, if we change our sample size back to 100 and we have 77 successes instead of 73, we just pick up that original interval and we shift it up here to the upper end of that proportion scale. So those are confidence intervals for a one sample population proportion. We've done it visually, we've done it by hand.